Okay, thank you. It's a pleasure to talk in your analysis seminar. I will highlight, there will be part analysis. The problem, however, that I'm interested in is motivated by Maass forms, which I'll introduce in a second. This is all joint work with Amit Ghosh and Andrei Reznikov. And I told Bob Langlands to come because, in a way, he worked on two things which maybe he never realized might be even related. One, percolation theory, and one, automorphic forms. They are related conjecturally, as you'll see, in a way that's probably quite natural, but not in a way that modular forms come naturally in percolation problems that I know. This is really about modular forms. All right, so let me set the stage of what I want to talk about. So I'm going to talk about the simplest cusp forms that exist. Now, I will in a moment tell you what they are concretely in terms of solutions of certain differential equations, so you don't need to know too much about modular forms except to know what the upper half plane is. So let's see, how does this work? So I'm going to talk about what are called automorphic cusp forms, which are everywhere unramified. These are the modular forms which are the closest to the Riemann zeta function. They are the two-dimensional analog of the Riemann zeta function, and there are infinitely many of them, unlike Riemann zeta function, which is the only L function in the world which is everywhere unramified. It's got a pole. These don't have a pole. And they are precisely the following object. So firstly, I will not vary the group, even though the techniques to prove anything here involve varying the group. But in describing the results, the group is just the 2x2 integer matrices of determinant 1. SL to Z. It acts on the upper half plane, which I call H, by the usual linear fractional transformation. Z goes to AZ plus B over CZ plus D if the matrix is ABCD, and ABCD are integer matrices. So SL to Z acts on the upper half plane. It acts discontinuously. And you form the quotient space, which is H over gamma, which has this familiar fundamental domain that you can find in any textbook in complex analysis or any textbook on elliptic modular forms. This space now, H over gamma, this will be X. Throughout this lecture, X is that space, and I'm only going to talk about that space, though to highlight some points, I might talk about a more general space in order to remind you what are general bounds from partial differential equations when we get there. So this space comes with a complex structure, because the upper half plane has got a complex analytic structure, and this group acts by automorphisms of the upper half plane Mobius transformations. It's also got a hyperbolic structure. And this talk is about Maass forms, everywhere unramified modular forms, which are, in fact, of the second type. They are associated with the geometry and not the complex structure. So this is a Maass space X. It's finite area. And the objects I want to look at are these functions phi, which I'll define in a second. But throughout this lecture, there's a very important curve inside the modular domain, which I'm going to make a living out of. So I want you to concentrate on this curve. So there's a symmetry of the modular surface. X was the upper half plane divided by SL to Z. It's got an extra symmetry, which in complex analysis never arises because it's anti-holomorphic. But in real analysis, it is an isometry. It's an orientation reversing isometry of this modular hyperbolic surface. It's the map induced from Z goes to minus Z bar. That's a map of the upper half plane, which is certainly an isometry. And it commutes, it normalizes SL to Z. So it means that this map is an isometry of the modular domain. Now that fundamental domain that I drew for you here, there's nothing canonical about this boundary. That was not a God-given choice. That's what everybody chooses when they choose a fundamental domain, but you could choose another fundamental domain. On the other hand, this set that I'm giving you here, which happens to be related to that boundary, is the y-axis, this geodesic. The circle mod z equals 1 on this segment, which is the bottom. So this is half the fundamental domain you saw before, but it's not this fundamental domain that I'm interested in. It's this delta 1 union delta 2 union delta 3. That is a piecewise geodesic curve. It's infinite length, but that doesn't matter. I'll call delta the union of these. So it's this curve coming from infinity down to here, from there to there, and from there back up. And it's important. It'll play a crucial role. It's the fixed points of this unique extra symmetry of the space that we have. And I'm going to make a living out of this. And in fact, the entire thing that I can prove here, that we can prove, will be based on the symmetry. So this is quite a special argument. All right, so now let me tell you what the objects that we're going to look at are. Their existence is by no means obvious. So a Maass cusp form, which is everywhere unramified, is a function which is it's defined on the Apophysis plane. It's periodic with respect to the group, so it lives on the quotient. So it's real valued in this case. You could make it complex valued, but it'll turn out to be real valued anyway. It's real valued. It lives on the quotient. It will be even with respect to that symmetry here. So I'm throwing half of them away. These are the most mysterious of all of them. These are the everywhere unramified guys. And they are solutions of this elliptic equation. This is an eigenfunction equation. This is the hyperbolic Laplacian on that surface applied to phi. Since Laplacian is, if you don't put a minus in front of it, is naturally a negative operator, it's better to write the eigenvalue equation this way so that lambda is positive. I don't want the constant function, so I'm going to assume lambda is positive, and I want the function to be square integrable. It's this square integrable condition, which is also equivalent to something called a cusp form, that makes the existence of these quite not obvious. In fact, Selberg got into the subject when Siegel was asking if such things exist. And he had the insight that maybe he could prove the existence of such a thing by computing a trace. And he developed a trace formula precisely for that purpose. That was the initial impetus for him developing the trace formula. I'll repeat that here. So there are many such cusp forms. They are precisely the everywhere unramified forms, and those are the topic that I want to discuss here. These functions phi as above. The numbers phi for which there's a solution, this is discrete. This cuspidal condition, which I haven't described, but happens to be the same as an L2 condition in this particular example. That's unusual. In the general theory, cuspidal is a much more robust and important notion, but here they're equivalent. I'm just in 2 dimensions. These lambdas occur with a certain, they're discrete, and Selberg was able to show from his trace formula, this was the only proof of their existence, that there are many of them, that they come with discrete numbers which are, if you count them, if n phi is I'm going to use this notation n phi a lot in a moment, n phi indicates that that's the nth eigenfunction of this type. They're ordered. Their eigenvalue increases, the n increases. There may be multiple eigenvalues for all we know. We don't expect that. They've never been seen numerically. But of course, if there's a multiple, then lambda will not change, but n will go from, you just count them with multiplicity. So the number increases. So they exist. They are fundamental in the modern theory of automorphic forms because they give L functions, which will play a side role, but an important role, as you'll see. Unfortunately, one of the main theorems will be conditional on something about an L function. So my functions are not only eigenfunctions of the Laplacian, which is how we started out, but they're also eigenfunctions of certain correspondences, symmetries, pseudo-symmetries of the surface. So there was the symmetry z goes to minus z bar, which was a genuine isometry. There aren't any other isometries, but there are isometries which come from finite coverings, which are called correspondences, and they give rise to these operators introduced by Hecker or Nodal, actually Hurwitz before, in a somewhat different language. Tn applied to the function psi is this sum here, sum over all integers whose product is n, b mod d, and this is a normalization that will be useful for later. Inside here, you see a linear fractional transformation, so this will commute to the Laplacian. The only issue is whether Tn commute gives you a gamma invariant function from a gamma invariant function. Gamma is SL to Z, and that's a very easy calculation that can be seen from many ways, and certainly due to Hecker in this clean way. These Tn's commute with each other. They form the Hecker operators, the Hecker algebra. We understand everything about these operators as algebraic objects, and the eigenvalues, the eigenfunction, we can therefore assume, without loss of generality, it might be automatic in this case, because the spectrum might well be simple at infinity, so that you're automatically an eigenfunction of all these Hecker operators. But if, God forbid, there's a multiple eigenvalue, then you must diagonalize. I will assume all functions are Hecker eigenfunctions. So that's an arithmetic input which is not clear what its role is as yet. Okay, from the title of the lecture, this lecture is about the zero set of such an eigenfunction. So we have an eigenfunction. The zero set of an eigenfunction is one of the first things that is always studied about an eigenfunction, from vibrating plates, from the days of Rayleigh. That's the nodal set. It's the place this function's real valued. It's where the function vanishes. I'll denote it by z phi throughout. And I'm going to show you a picture now of what such things look like for these. They have been computed in many, many examples. The complement, if you take the manifold, which is my modular surface here, and you remove the place where it's 0, you get a certain number of connected components. Those are called nodal domains. And their number is what I want to address in this lecture. It's very mysterious. All right, so here's a picture. The first person to successfully compute a highly excited, or any actual such Maass form, is Hedgehog. Cartier got interested in this and led to some very weird things about the Riemann hypothesis, some false ideas early on. Hedgehog then got really interested in this kind of calculation and made the first genuine correct calculations, and this is the biggest one that he ever computed. He used the Cray. This was in the late 80s, early 90s. He used the Cray. He can't give me any data. He says the machine is burnt, doesn't exist anymore. Nobody uses supercomputers anymore. And there are physics computations for the modular group, but I trust them much less. I trust him completely. And this is the biggest eigenvalue that he was able to compute. So I'm going to use the notation always that the eigenvalue is a quarter plus, I'll use t squared. So the lambda is very big. And in this picture, which he had shown me and many other people in the early 90s, you see the zero set. But what can you say about it? We had no tools to really address any question. In fact, it wasn't clear what you want to say about it, other than...
Can you tell us where the lower boundary of the fundamental
Yes.
domain is?
Yeah. It's this. Sorry. So all the symmetries, or anybody who you recognize in that picture. By the way, this picture, you can see this on the memorial for Selberg in the AMS volume. They have in the cover a picture, which is basically this. This was the only picture on Selberg's walls that were found after he passed away. Was this and some variants of these pictures. Here's the boundary. The one thing that you would notice here, and it's sort of clear that something like this should be true, is that the nodal, I don't know whether he cheated here or whether he really resolved that. They come close to crossing, but they never do cross. And that's what you should expect. You can't solve this problem explicitly. It's a misnomer that you can write down automorphic forms in closed form. You can write down one or two modular forms in terms of the delta function or something, but these kind of things are given in terms of data that we are very interested in and quite random in their own ways. So it is given, and I will use this eventually as some Fourier expansion with coefficients which have all the arithmetic information in them. But this is a numerical computation, and from the numerical computation it looks like the zero set, this nodal line, is non-singular. I have no idea how you might even touch proving something of that nature. It's just way too hard. So we'll have to accept that these things may touch, though they never seem to touch in any numerical experiment. All right, so this is the kind of picture that has been around for 20 years. And I have often wanted to say something about this, and that's what this lecture is about. Before we try address what we're going to say about it, let me remind you what is known in general. This problem is sufficiently hard that you go and work very hard on it, use all the structure, and then you find, but this is known in general. So you better keep in mind what are general facts about an arbitrary Riemannian two-manifold. So I'm going to stick to dimension 2 for simplicity. I'm on a Riemannian two-manifold, and I'm looking at the eigenfunctions of a Laplacian. There's some general facts that one should keep in mind that are going to apply handsomely to our example, because it is, after all, a real analytic two-manifold. The fact that it's not compact, let me suggest you ignore for the time being. That's an issue we understand very well. The most famous and still the best theorem about nodal domains, how many connected components are there, is the upper bound of Courant. It's not sharp, but it's a beautiful global inequality. It takes, I remind you how it's proved. You found this in Courant-Hilbert. This, of course, was a book written by Courant and Hilbert. I suspect Courant wanted to put all his theorems in there. So it's highlighted over and over again in the first few chapters, and it's a great theorem. It's his famous theorem, I guess, written.
That leaves him open to the suspicion that the theorem is Hilbert's.
No, listen. Okay, maybe. It's a great theorem, and it's very easy to prove, and it's based on a global minimax argument. So the eigenvalues of a matrix can be written, the smallest eigenvalue is the inf of some Rayleigh quotient. The next can be written as a min-max inequality. And by using that, you can easily give this upper bound by min-max argument. So it's a very useful, very clever application of the min-max principle, is the standard proof that he gave. And it's, in order of magnitude, probably sharp in some cases. That is, there are examples, and our example is going to have this feature conjecturally, that the number of nodal domains is at most is roughly, in some cases, about the eigen number. But it's never more than the theorem says it's never more than that. So that's the global upper bound. More recently, there was a nice piece of work. Zeldich is the master of complexifying anything that you see. So I'll give you the proof in words in a second. And their theorem is the following. Suppose you take a planar domain. So now it's a domain in the plane with a boundary, which is, I'm now talking general theorems. So I'm in the plane with a real analytic boundary. Okay, then Courant's theorem will apply for the number of nodal domains. You could ask how many nodal domains meet the boundary. There should be fewer, presumably. And the upper bound that you can prove is that if the boundary is real analytic, then the number of intersections of the nodal set, Z phi, with the boundary is at most a constant times the square root of the eigenvalue. T is always the square root of the eigenvalue. So the number of boundary nodal domains is at most square root of T. And remember, Courant's upper bound is basically lambda. N is about lambda up to a constant. So how's this proved? Well, it's very hard to give upper bounds for real zeros, but if you complexify everything inside, that's where you've used the boundaries real analytic. So you complexify into a tubular neighborhood. And then the number of real zeros on this curve is related to the number of complex zeros of the new function. And then you can use Jensen type inequalities. The important thing here you might be asking, how do I know that this was a Neumann boundary condition? The normal derivative is assumed to vanish on the boundary, and now I'm saying how often does a function vanish? You can't have both the normal derivative, this is the Kaliman estimate, you can't have the normal derivative and the function both vanish everywhere without the function being identically zero. So you know that already there are only finitely many places where it vanishes, and this is a sharp upper bound basically, meaning it can happen that there are that many intersections. So this is a nice complexification argument. These are both upper bounds. There's a lovely conjecture of Yao made here in the Institute when he was here for a short period, that the length of the nodal domain, we are in a Riemannian setting here. So the nodal domain, assume the original thing is compact. So the nodal domain has a certain length. The length behaves nicely. His conjectures, the length is bounded above and below by, this should be a T sub phi, the square root of the eigenvalue. So if you go back to that picture up there and you look at a compact piece and you compute the length, it will obey this inequality. Now Yao conjectured this for a smooth surface, and it's not proved. It's a wide open important problem. But if it's real analytic, then using kind of complexification arguments, it was proved by Donnelly and Pfefferman. So it's a remarkable fact that the length, now remember the length is a local quantity. You can compute the length of a curve by adding up the local lengths. It's not a global quantity like the number of nodal domains. That's the topology of the zero set is a much more subtle invariant. So anything which is local, one has local bounds which are roughly correct. So not only is this an upper bound, it's also a lower bound. So keep in mind that set we were looking at, we know some things about it. It's becoming dense, we know its length, we know that upper bound for the number of nodal domains. Another two, what I would call convex, or they're interesting inequalities. When I say Homanda here, Melrose always likes to tell me that it was proved actually by a Russian Abramovich in the second order case. Homanda generalized all second order stuff to nth order stuff, but it's well written in Homanda's treatment, and it's the one everybody follows, so maybe I stick to Homanda if it's okay. In his proof of the Weil law with his remainder for a general Riemannian manifold, his methods immediately give an L infinity bound. So I have my eigenfunction. Throughout this lecture, the eigenfunction is always normalized to have L2 norm 1 on the whole space. You can ask how big does the function get at a point in terms of the eigenvalue. If you use some Sobolev kind of estimates, you'll get very weak bounds. The much better thing to use is, this is relying on microlocal analysis. That's what Homander was doing in this analysis, following Lax's construction of a parametrics. This is all local. You can show that the eigenvalue, the maximum that the function can be at a point is at most the square root of my parameter t. This is all in dimension 2. Not only is this a good bound, but it's sharp on S2. So if you're on the S2, there are spherical harmonics which get this big. One of the things that we're going to be using, you'll see why in a moment, is not just the restriction of the eigenfunction to a point, but the restriction of the eigenfunction to a curve. So I'm going to concentrate on a geodesic segment, which is the most nasty curve to make an estimate on from microlocal analysis. And you could ask, could you do better when you restrict, so I take phi, I restrict it to a segment of a geodesic, and I ask how big is the L2 norm? So of course the L infinity norm is at most t to the half, so the L2 norm is at most t to the half, but the restriction to a geodesic can be improved. This is again a local bound, t phi to, that's a quarter over there. And again it's sharp on S2, so these are all sharp on S2. So these are 5 general facts and the most relevant and pertinent ones that should be kept in mind. Anything I state, if I don't do better than this, then I'm guilty. Because what's it got to do with modular forms? Okay, so that's the setting. I now want to tell you a conjecture which Bogomolny and Schmit, Bogomolny is this really brilliant mathematical physicist who makes fantastic conjectures. He's also the Bogomolny from Yang-Mills theory, Bogomolny equations, but he turned to the behavior. He's very interested in the behavior of eigenfunctions in quantizations of classically chaotic systems. And that is the signature of our system. Our system, if you look at the geodesic motion on this hyperbolic surface or on any negatively curved surface, the classical mechanics is very chaotic. And being so random, you can't write down the eigenfunctions. Maybe something different, there's a different kind of behavior. And let me tell you what his remarkable conjecture was. And until I checked it myself, and I have some undergraduates who have checked this kind of thing thoroughly, and I now have complete faith in the first step of his statement, is the following. He says, suppose you have a classically chaotic Hamiltonian. So you can forget my hyperbolic triangle, which is where we're working up until this point, but you could go in the plane and have a billiard inside. The classical mechanics would be the billiard inside this domain. Suppose that's chaotic in every sense of the word. Then he says that the eigenfunctions will behave like random waves. So this is a general principle which is far from provable, but this is a meta statement. It's not unreasonable. He's not the first to suggest that. Berry suggests that, I think, more clearly. Then you could ask, if I give you a random function, a random wave, I'll tell you in a minute what that means, how many connected components does the zero set have? So maybe the answer can be gotten by understanding something random. So there are 2 sets of wild fantasy here. The first step is to say that the eigenfunction in a chaotic system behaves like a random function. Random with some scale related to the eigenvalue. The second thing is what is true for random functions. And even that's quite mysterious, but he makes both these steps. And especially with the second step, I will explain at the bottom here, he introduces a percolation model, an exactly solvable bond percolation model, which I'll define for you in a second, which by quite a miracle was solved exactly by, it's one of the few exactly solvable critical percolation models, solved by Baxter, maybe Temperley and Lieb before him in some form, from which you get a number. Now these conjectures, you could argue about all this heuristics, but in the end he's got a fantastic statement. And my interest started in this when I checked his statement for the modular group. I'll show you how I checked it in a second. But before I tell you what, so this is his exact conjecture, that the number of eigenfunctions in a chaotic system So if it's the nth eigen, the number of nodal domains for the nth eigenfunction has this miraculous constant. Now, nobody's going to write a number like that down without some deep insight and be right. I mean, it's not like he gave this number to 6 decimal places. He wrote down this exact number as being a universal to all 0 sets of random functions, which is probably true. Okay, so this is a conjecture which is quite remarkable. It's like much more striking than Weil's law. Weil's law tells you how many eigenvalues there are than less than x, and that's a very general statement for a Riemannian manifold. Here this is false if you're not chaotic. Here we're in a chaotic system. He's telling you that each eigenfunction has this many nodal domains. And so it's not Courant's upper bound, but it's this small percentage of this. This is a rather small number, by the way, if you look at it for 2 minutes. It's positive. So that's a conjecture, and the conjecture comes from various heuristic leaps of faith. And let me just tell you where a Bond percolation model comes from in his reasoning. Imagine that I was on the square. I know Jean likes a square. In his Fourier series, you can write the eigenfunction as sine nx times sine my. What? On a flat torus, yeah. Well, that's even more you like. You don't even want to think of the boundary. Okay. So if this were a flat torus and you were looking at an eigenfunction where n squared plus m squared were the eigenvalue lambda and n and m were roughly the same size, then you'd get a checkerboard picture like this for the 0 set. So notice this is very singular, very different. They cross each other. But imagine I randomize this by adding a little term. Or imagine that whatever my random model is, it makes a serious perturbation of this. But the perturbation I want you to think of is at each edge, at each node here, each vertex, if I have to decide, because I'm not allowed to cross, so if I'm not allowed to cross, these curves are either going to go this way or that way if I perturb it a little bit. And I do that independently at each site. And when I'm done, I ask how many components are there. And you can translate that into what's called a Bond percolation model at a critical percolation model, meaning the probability of choosing this or that is a half a half. That's what makes it critical. And there are very few exactly solvable percolation models in the plane, and this is one of them. And that gives this number for the number of components in that purely random problem. This is for the square. This is not for a triangle. This is not a universal thing like conformal invariance. So you might debate why was the square so important? No explanation is given to this. Nobody knows. So you could ignore this, but you can't after the next slide. All right.
So what is proof for purely random?
I'll tell you at the end what's proof. I'll get to that since I put it in the title. So I was, for many years I ignored him, but after QUE was proved, I'm going to tell you what QE is. And when I decided I'm going to try look at this problem, so Ghosh and I decided, let's count. You can look at Hedgehold's picture there, which is in his paper. You try count the number of nodal domains there. Your eyes start to go cockeyed. So I went and I just colored it in. This took me a good few hours. I enjoyed it. It's kind of good therapy. It's like in primary school, I colored it in. It's too colorable. That's an IQ test. Why I only need 2 colors? Because the components are phi positive and phi negative. The 0 set, you only need 2 colors, so I just used black. Okay. And then I counted 58 nodal domains in this area, and I localized a bit here, and I checked it against Bogomolny's conjecture, which is local, agrees to 3 decimal places everywhere. Well, if he's predicting a number that the modular forms know about from percolation, it's compelling. Okay, so you can take it with a grain of salt, but at that point I was a converted guy. There are other spectral problems where you can check this on spherical harmonics. I'll return to that, where a student of mine in an undergraduate thesis says, check this conjecture very thoroughly, unlike their numerics, which were not so convincing. And this, his conjectures for the number of nodal domains seem very accurate. He goes on to relate it to SLE and stuff. That seems way off. But this seems very robust. So there seems to be a universal number, and it seems to be modular forms know how many nodal domains they're supposed to have. Okay, and that's what we're after.
So it's not connected to SLEs in numeric when you do numeric?
It doesn't agree. He says it does, but
Who says it?
Bogomolny, but when you look at it, the data doesn't look so good. And then he tries to change it, and the only thing that's the variance was even wrong. My student found his variance was wrong. How to fix it up, we've discussed, Peter and I. It's not clear. But this seems, every experiment gives exact, there's a universal constant for the number of connected, for the topology of the zero set of a random function, which you should think of as a random plane, real plane curve. How many ovals does it have? I can explain that. But I don't want to go into random here. So this seems correct here. It's too colorable. Now, if you want to prove something, I gave you some general facts. There are also some facts that you should be warned about. You're not going to find it that easy to prove there are many nodal domains, because Courant already worried about this, and one of his very first students, Stern, from his 1925 Göttingen thesis, which I wasn't aware of, but Zev Rudnik pointed this out to me. It's in Courant Hilbert as a highlighted picture. That's the picture. I colored it in. This one was easy to color in. Is a torus, a flat torus, the one that John likes so much. And he constructs a sequence of eigenfunctions on a flat torus with bigger and bigger eigenvalue on the ordinary standard flat torus for which there are only two nodal domains. So there was an upper bound that Courant gave, but there's no lower bound that's going to causally be there. What happens is it's like a jigsaw puzzle. It just breaks into two cunningly. So he takes the standard sin nx, sin m. He takes n squared. He writes lambdas in two different ways as a sum of two squares. And he takes the first guy plus epsilon times the second guy, carefully choosing the epsilon. And this is the shape of the nodal domain. So there is no theorem in general, or there's no local theorem about making many nodal domains. If there are many nodal domains, it's a global statement. This is about the topology of the zero set. It's a much more subtle thing, and nobody's really studied it because it seems very difficult to say anything, even in the random world, which I'll return to. But let me stick to this deterministic world. Okay, so now I'm going to tell you what we can prove and how we prove some of these things, and in the end I'll say a few words about random issues. So remember, I'm going to exploit, I haven't shown you how yet, I'm going to exploit completely this symmetry. So our eigenfunctions were even about this, they were even relative to this unique symmetry of the fundamental domain. And I've defined that delta, it's the same set as before. Correspondingly, my nodal domains are going to be called inert or split, depending on how they behave under the symmetry. And the behavior you'll see is very similar to issues of inert and split in the theory of numbers. So a nodal domain is inert if I take a nodal domain and I apply the automorphism sigma, the sigma of that nodal domain is again a nodal domain of the same eigenfunction. You can show that easily enough. So the nodal domain is either, and because the nodal domain is the biggest connected component, either the sigma will take me precisely back to what it was, or they will be completely disjoint. So it either is inert, so it's completely fixed by this automorphism of order 2, or it's split, in which case the automorphism has, there are two of them which are distinct. And you can see it in the following picture. All right, this is from my paper with Ghosh and Reznikov, which is almost ready. I learned from Ghosh something fantastic that he learned from his daughter, that you don't have to color these things by hand, you can press paint. You just pull this up on the screen and you pull up something and it says paint, and it paints it. I prefer my painting, but still. All right, you might, why does he need 3 colors? What's he doing? You know, you only need 2 colors. Well, it's just to show you the split ones. The green ones are split, so that guy and that guy, the automorphism took you from there to there. This guy's split. This guy, the automorphism takes you back to itself. So as you can see, the number of domains breaks up into an even number of split ones and some number, which I don't know, of inert ones. And the total numbers is the sum of those two. And in this particular picture, you see that there aren't that many split ones. But that's just simply because the eigenvalue is, even though Hedgehog went so far out, he hasn't gone far enough to see what the truth, as you'll see in a second. Okay, so that picture tells me what the next definition is. I pressed the wrong thing. So the inert, so I'll let Ni of phi be the number of inert nodal domains, and Ns the number of split. And clearly the total number is the number of inert plus the number of split. And now I must make my confession is I have no idea how to make a split nodal domain. I mean, numerically you see them. You'll see that most of them are supposed to be like this. The entire name of the game here is I'm going to, so the aim of this whole lecture and the whole project is to prove the number of nodal domains grows, not as fast as Bogomolny conjectures, but that the number of nodal domains goes to infinity. That's the big theorem. And we will achieve that by only working with the inert ones. Unfortunately, I don't know how to deal with the split ones. And the reason that I can do anything with the inert ones is this topological proposition. After all, this is a global statement that we're making about the number of connector components. So the trouble is, if you look locally, as hard as you want to look, how can you tell that the thing doesn't come around itself and break into just a few components? Well, here's one way, discovered by Soden and Nazarov in the random world, which I'll return to when I explain the end, is maybe you can find a nodal domain which is a little loop locally, and then you're done. And in fact, they make all the mileage out of that. But that technique of what's construction of a barrier is not something you can do in an explicit world. That's a purely random statement. I'll explain that connection later. So here we use the only other device that I think I've seen, and this is the device we're using, that let this integer here, so I'm going to describe to you that the eigenfunction can't vanish on this curve delta, this key curve delta. Everything is going to reduce to this fixed point set of the symmetry. So delta was a piecewise geodesic 3 segments. As I traverse around this geodesic, I look at the sign changes of the function of the eigenfunction phi. Well, the first thing you might shout at me, why doesn't phi vanish identically? I'll prove that to you. As I go around, it'll change a certain number of times. Everything's real analytic. That number I call kappa of phi. And basically, the number of inert domains, so this is a purely topological statement, is about 1/2 of the number of sign changes. So at least if I want to produce inert domains, it's sufficient for me to produce sign changes. And it's at most the number of intersections. In fact, this is almost certainly equal to that. This will equal that if there are no intersections, no crossings. As I told you, that's hopeless to prove. But luckily for us, the inequality only improves if there's a crossing. So if I want to give a lower bound for the number of inert domains without knowing that I'm in a generic position, because I can't know that, what I'm saying is if by some coincidence I don't break one of those crossings, I will only have more nodal domains, not less. That's an easy exercise, and this is an easy exercise in topology.
So I didn't understand. You expect to have more inert?
Yeah, you'll see in a second. You expect to have much more split.
Much more split.
Right, but the only guys I can look at are inert, so I'm going to produce way too few from Bogomolny's point of view. But I'm going to produce infinitely many. All right, so that's the aim, and this is going to be the passage. So this now converts the problem from understanding. This allows me to go down a dimension. That's where this curve is used. I need to look for sign changes of phi around this curve. If I can produce at least one sign change or many sign changes, I'll have produced inert nodal domains. I can answer your question. Well, I'll answer it in a moment. So this leads to a separate issue, and the issue which is much more tackleable, and that is restriction of eigenfunctions to subsets. How do they behave rather than this global question of how many components there are? And this has been studied by many of us for many years. Let me review what I'm going to use. So I have my manifold X. I already gave you the general theorems that are relevant of this type. So if I have a surface X and I restrict to a curve, I can ask the restriction, how big is the eigenfunction when restricted to the curve? So first I'm going to discuss mainly upper bounds, but the first theorem is actually also a lower bound. So suppose I restrict to a very fat set. So I restrict to a set which is like a little ball inside the manifold. So I look at the L2 restriction and I ask, how does that behave? This is essentially what's called the quantum unique ergodicity conjecture of Rudnick and myself, which was solved quite brilliantly by Lyndon Strauss with a final technical thing missing that was done by Soundararajan. So this is a known theorem which reads as follows. What's quite interesting about the proof is all the techniques that go into it, besides the arithmetic techniques which are everywhere embedded in this, are techniques of measure rigidity and ergodic theory, which are going into this proof of what is a very soft statement, but I think very deep. And that is, if I restrict phi to a ball, or to any nice positive measure set, then the L2 restriction will converge when the eigenvalue goes to infinity to the area of B over the area of X. In other words, the mass that it gives to the set B is roughly just the ratio of volumes. In particular, it doesn't go to 0. So if B is a ball and it's fixed, the mass can't disappear on you on that ball. It's everywhere. This is I'll be using over and over again. So this is a deep fact. It was known to follow easily from what's called Lindelof and subconvex estimates, but an unconditional proof was a very fine achievement, really. The key ideas were in Lindenstrauss. This just stopped the escape of mass. So this is a restriction theorem to big sets. Suppose I restrict to a point. Restricting to a point is a L infinity norm if I vary the point. So there, you're not going to have a behavior that an eigenfunction restricted to a point is universal. It could be 0, it could be anything. But maybe it's not too big. And I told you the L infinity norm of Homanda was t to the 1/4. And many years ago, Vanish and I, actually it's the first paper where the method of amplification was used successfully to prove something new, we're able to give you a bound better than Homanda. 5/12 is less than 6/12, which is 1/2. I'm highlighting that not only because I like the theorem, because I'll use it. Precisely that improvement will open the door to prove their nodal domains, as you will see. And finally, what is the truth here? I just want to point this out because this is an analysis seminar and not everybody knows what the Lindelof hypothesis is. And unfortunately, in the main theorem, I will make an assumption that the Lindelof hypothesis is true. These are apples and oranges, so I don't feel too bad about it, but it would be nice to get rid of that. So let me remind you what the Lindelof hypothesis is. So suppose I ask about this L infinity norm, which Ivanic and I have a subconvex estimate here. The maximum is never bigger than 5/12. The conjecture that we have here is that the maximum, if you restrict at least to a compact set, is never bigger than t to the epsilon. It's not bounded. The eigenfunctions are not like sin nx and cos my in a chaotic system, but the claim is they don't grow faster than any power. So that seems to be true, but if it's true, for all those PDE people who want to go work on this, and I'm afraid I did this to Kathleen Morovitz. I gave a colloquium, AMS colloquium lectures. I put this up and I said improve 1/2 without using arithmetic, because you will be proving something about the Riemann zeta function secretly. And she's been doing that since, trying to do it. But the effort put into it with all sorts of ideas, but I'm afraid none of them have worked so far. So this is a hard problem. And I can tell you it's hard because this conjecture implies the Lindelof for the Riemann zeta function. So this shows that the Lindelof hypothesis, unlike the Riemann hypothesis, is a conjecture which is much more robust. It comes from estimates for partial differential equations. But it's not true on the sphere. So the key input here is that the negative curvature, which Bergen doesn't believe this conjecture, but he's never found a counterexample. I'll have my head roll if you make a counterexample. I'll get such misery from your counterexample. I'm happy, but I have to see the counterexample. Okay, whether it's true or not is another matter. We're in negative curvature. This is the conjecture. That's the only improvement of the bound. The Lindelof hypothesis is that the Riemann zeta function grows slower than any power on the half line. It follows from the Riemann hypothesis, so don't question this conjecture. The last one. You can conjecture ours, but not that one. Yeah.
Do you need that for all three or just most?
You need it for 1 point. It's actually for the Eisenstein series at one God-given point. Yeah, at I. In other words, you don't need K to be a compact set other than a point. But I'm lying, if that's what you mean. Yes, so you need this for the Eisenstein series where everything is similar. I just didn't want to introduce the continuous spectrum into the lecture. Okay?
So you're saying there's a particular phi?
There's a particular continuous spectral guy for which is the same conjecture. Everything's the same. Everything I've been saying here is also going to be valid for the Eisenstein, unitary Eisenstein series. And then you apply it to a specific Eisenstein series, a specific point. So this is not a two-way implication as far as we know. This implies that. That certainly doesn't imply that in any understanding. since I believe they're both true, you could say A implies B and B implies A by different proofs. So I'm not expecting you to show one's true and one's false. They're both true. Very recently, just last Friday, and then Marshall was giving a lecture here, and he announced an improvement of the restriction in this modular case, better than Burke and Reznikov. So remember, t to the 1/4 was the bound when you L2 restrict to a geodesic. This is a slight improvement. 3/12 is a quarter. That's a slight improvement by using the method of Vanish and myself and some harmonic analysis. All right. Now let me get back to the nodal domains. So what I've explained so far is that we're going to try to produce inert nodal domains by trying to make phi change sign on this particular curve, delta. So the first thing you should tell me is, why doesn't phi vanish on, can you tell me which curves phi might, maybe if you looked at that picture, you might have noticed you don't see the 0 set containing any geodesic, any horocycle, or anything that you recognize. And that's a theorem. So let me give you an easy theorem. Before I start giving upper and lower bounds, so I'm going to have to do something much harder. I have to give a lower bound restriction instead of an upper bound restriction. And to do that, I should somehow first know that phi doesn't vanish identically. So let me give you a very easy dynamical theorem. Suppose that I have an eigenfunction. I claim it can never vanish on a segment of a horocycle or a segment of a geodesic. Never. Okay, why? Suppose I have a horocycle. Any segment of horocycle. By analytic continuation, it will vanish on the continuation of this horocycle to infinity. On the quotient, this horocycle, by the dynamics of horocycle flow, is either periodic, in which case I'm going to prove much more, as you'll see, but you can give an elementary proof, or by unipotent dynamics, it's dense in the unit tangent bundle, so it's certainly dense in the space. So phi restricted to a dense set, phi is analytic, must be 0, but phi has L2 norm 1. So that's not possible for phi to vanish on a horocycle. The horocycle is a practice problem here. Just let me make that clear. The geodesic is the way I'm going to produce nodal domains. So, but once we started to look at this, we wanted to understand what can you say about sharp restriction theorems in this context. So for a geodesic, the argument's a little different. Our function phi is already even about the reflection in the delta 1, delta 2. So half the fundamental domain, which happened to be the fixed point set of this extra automorphism, is also the following. If I look at the hyperbolic plane and I look at the group generated by reflections in the y-axis, that's delta 1, in this mod z equals 1, ordinary reflection, and the third reflection, that's called a triangle group. And that's that's bigger than the modular group because it's got orientation reversing symmetry. So it's the normalizer in the full isometries of the plane of the modular group. Our function phi is already invariant under that. We know our function phi doesn't vanish on those curves by Kaliman. I mean, you can see it many other ways, but it follows from that. Now, suppose it vanishes on some other geodesic segment, then it will vanish on that whole continuation of that geodesic segment to infinity. And that will mean that by the reflection principle, the function is either even or odd about that. So phi squared, you first argue phi squared is now invariant under a much bigger group. It's a group generated by these three reflections and then one more reflection. Now, it's well known that the modular group with this reflection group, this triangle group, is maximal, discrete. If you throw in any other element, it will become non-discrete, and then you get a limit point, and then from there you start to build up a curve by renormalizing, and eventually you get that your eigenfunction is invariant under a one-parameter subgroup, and then you use separation of variables to learn that the function has to be 0. So it's completely elementary, but it's not effective because you analytically continue. It doesn't give me a lower bound. So I know these two facts, the most important one, that I cannot vanish on a geodesic segment here by this very indirect group theoretic argument with maximality, or that should be maximal, of the modular group, or at least this reflection group, but no estimates. So now I want to state the new theorems, which will allow everything to work. So these are sharp restriction theorems that we prove in this paper for the restriction to a closed horocycle and to a closed, and to a geodesic segment. So this was until recently conditional on a stronger form of quantum unique ergodicity, but it seems our proof now actually will only use Lindenstrauss's work. So I will announce it here. That should be a little t. I think Mumford introduced the notion of a theorem with a little t, meaning the details still need to be completely checked. The theorem is a bit better than I had in mind last week. So the theorem is a capital T with a slightly stronger assumption, but without that, which is much more natural, it makes the slide much more beautiful. This, I'm claiming, is unconditional, but there's a little reservation there. So the theorem, let me review what it says. So fix a closed horocycle on the modular surface. Restrict any of our eigenfunctions to that. I hope I've convinced you that phi should not be identically 0. I'm saying that actually the L2 norm is not only not 0, but it's basically bounded below by t to the minus epsilon and above by t to the epsilon. This is heavily involved in arithmetic proof, heavily arithmetic proof, using symmetric powers, using everything available that we sort of have from the theory of modular forms in the upper half plane. Now, let me restrict to the geodesic. Beta is a geodesic. So this is what I'm really interested in. Beta is a subsegment of my curve delta, which is going to produce nodal domains, we hope, inert nodal domains. I have to make beta sufficiently long. Our proof, which is unconditional, that's one of the insights here, is not to fix beta to be short, but to allow it to be still compact, but long enough. We're now playing constants against each other, which is what the new idea was. All right, then the claim is that the restriction to beta of the eigenfunction, which we know I've convinced you it can't be identically 0 by Kahlemann's estimate, but in fact I'm telling you the L2 restriction is bounded below by a universal constant and above by t to the epsilon. So these, unlike all the previous theorems, are sharp theorems. In other words, up to the power, these are absolutely sharp.
What do you mean by sufficiently long? Does it depend on
No, it's universal. It's universal. But it can't be actually very long. It's probably, the proof involves constants, and then you have to use the length to beat the off diagonal by the diagonal. You could imagine how that's done. All right, so immediately from this, I'm going to show you this argument in the other context. I want to give you one cute little proof. You get that the number of sign changes, the 0 set, will meet any horocycle. Okay, so an upper bound for how often it meets a horocycle can always be given by complexification once you have a weak lower bound. So in fact, this upper bound is true without arithmetic, and it's a nice theorem of Jung, who's a PhD student at Princeton. So this upper bound is much softer. The lower bound is what comes from all this restriction and from some argument I'm going to give you. Jean has improved this exponent. If I ever show him anything, he's very quick to improve it, so I stop showing him anything. I haven't checked the details, but he thinks he can double this exponent. In this case, this is not the case that's in my old exponent. Yeah, I haven't checked exactly. I'm sure you're right. Yeah, you were using Holder spaces instead of L infinity, which I'm going to use here. But for the geodesic, I don't see any hope of making that argument work, so I wanted to state them together here. And that's the big, this is the main theorem. Assume, unfortunately, and I'm going to show you why I have to assume Lindelof, not for the Riemann-Zeta function, but for the standard L functions of modular forms. Now, it could be we live in a world where the Riemann hypothesis is true for some kind of L function and not for another kind of L function. If that's the case, I'm out of here. It's not the world I want to be in. All right, that I can't accept. It's this Lindelof hypothesis follows from the Riemann hypothesis. For this, that's all about the zeros of an L function, which is a much better understood than the zeros of a Maass form, which is what we're trying to understand. So I don't view this as too bad, but unfortunately I have to assume that, and you'll see why in a second. The upper bound is a soft thing, that's unconditional, but the lower bound is where we're using Lindelof, and let me show you how. So how I'm trying to produce sign changes as I go around phi for the function with the aim of eventually producing nodal domains. So the formula for the L function, there are many formulae for the L function. They can be given by integral representations. This one's very reminiscent of Riemann's formula. It's due to Hecke in this context. And that is if you actually take the geodesic 0 infinity and you integrate phi of I y against y to the s dy over y, if any of you have looked at Riemann's paper, that looks like the integral of the theta function against y to the s, giving the completed Riemann zeta function. So this Hecke observed is identical in this context. And that gives you this standard L function. So using this Lindelof for this L function, one can show that the integral over any short interval, so beta is my long segment for which I have a lower bound for the restriction of the L2 norm. If I integrate from alpha to alpha prime the phi of I dy, and you compute what the size of the Archimedean factors are, yeah, you'll get that this decays like t under Lindelof. This is where only place Lindelof is used. Decays like the eigen square, this t phi to the minus a half. Ignore the epsilon. That's just a safety valve, which is necessary. So because phi is a highly oscillated eigenfunction and is not vanishing identically, it's not, forget the second thing, you don't need that. The integral of phi should cancel because it's oscillating. And this picks it up, how much it cancels. To get a sign change, I'm going to use the old argument of Hardy, when he first proved that zeta has infinitely many zeros on the line a half. I'm going to compare the integral of phi and the integral of absolute phi on short intervals. If they're different sizes, the function is real. It had to change sign. Okay? So that's how we're going to produce sign changes. And it's this part that John says, has an idea with using other spaces. But in this case, I don't see that it would help. Okay, so the integral of the absolute value of phi on this long segment for which we have a lower bound on the L2 norm is anyway equal to the integral of the sine of it times the integral of phi over these segments. If the L sign changes, I'm trying to give a lower bound for the number of sign changes. So this is an identity. And this is less than or equal to the number of sign changes. Now on each one of these, according to that, this decays like L, the L of them times t to the minus a half. On the other hand, the mean square of this function, the main theorem we've proved is that the mean square, the L2 restriction, is bounded by 1 from below. And that's at most the maximum. So this is where you might use better technology, but I don't at this point see how. It's at most the maximum of the function over this interval times the integral there. So the integral of a beta is that, and the maximum I have to put in the best bound I have for the maximum. If you put in the convex bound for the maximum, you'd get absolutely nothing out of this argument. But you put the subconvex bound that Vanish and I proved, that opens the door and gives you t to the 1/12. So that's where the lower bound for the number of sign changes comes. And at this point, you should be happy that there are, together with the topological lemma, the number of inert nodal domains. Okay, the complexification argument gives you that the number of inert nodal domains in a compact region is at most t, and the totality of them is at most t log t. Okay, what is Bogomolny's conjecture? That this number is a constant times the eigenmode number, which is t squared, some constant times t squared. I mean, Bogomolny is giving us an exact constant. In any event, or the totality of inert nodal domains is only about square root of all the ones that you're looking for, according to his conjecture. I don't know how to produce any of his, but he's saying most of them are green in my original picture. They're about, if you go with t very large, there'll be about t squared green ones, and I know they are at most t of this type, and I'm proving, what?
Does he give an argument for that?
No, that's his conjecture.
Why?
No. So he says that the number of nodal domains is modeled by this percolation. I'll get to that. Okay. I'm going to spend the last 5 minutes on probability, if you want. I'll skip the proof of this, which I have here. I was going to outline the hard part at one point, but I was just...
I mean, you're saying it just comes from percolation or something?
Yeah, percolation prediction gives that. And that's his conjecture, that there are a tremendous number of nodal domains. In fact, the universal constant times the eigenvalue, and the constant he even gives, and numerically it looks absolutely correct. So most of them are green, if he's right. I don't know how to produce any green ones. My aim was just to produce infinitely many nodal domains, and even that was done a little short in that we have to assume Lindelof, and then we're producing t to the 1/12 inert nodal domains by the argument I've given you, which is going to infinity. It's not the right exponent, obviously, and improving it would be interesting, but we're nowhere near the truth. At best, if you put in all sorts of conjectures, you'll get up to t here for the number of inert ones, and that's the right number of inert ones. If you've ever counted primes in your life in a number field, and you count the inert primes and the split primes, there are many more split primes, square of the number of inert ones. It's exactly like this. So the point here is that the technology that we are developing here is very crude to go from local to global. To go from local to global, I insist on using this fixed set where I can actually look for sign changes to produce the global domains. I should say also that if you go high in the cusp, you can do much better because there the eigenfunction separates into a product function and you can analyze things very, very accurately. And so all this was about making nodal domains in Hedgehold's picture at the bottom in a compact part of the fundamental domain. And that's what we have achieved. All right, so keep on pressing volume. I'll skip the proof and can show anybody, not the proof, the one idea of the proof, but I want to discuss what it is about random. So let me go back now and just go back to percolation and tell you what you can or cannot prove in our present understanding. So this, when I should actually tell you one word here. The eigenfunction phi has an expansion. It's periodic. There's an element in the group z goes to z plus 1. So the function's periodic in z. And because an eigenfunction, it's got a coefficient, which is all the arithmetic. That's where all the Hecker eigenvalues are. That's where all the number theory is, if you wish, of this Maass form. It's also got this Bessel function, which is the solution of this ODE in separation of variables. And so when you want to understand what phi looks like, either locally, globally, where it's 0, and all this kind of issue that I'm describing, on the y-axis, we're looking at this series. This series rho phi n, y to the half. The arithmetic there, it's sort of a little bit separated from the analysis, which is the behavior of the K-Bessel function. The K-Bessel function has been studied for 2 centuries. It's a fantastic thing, and the uniform asymptotics is very delicate. It comes with 3 ranges. So remember T, the eigenvalue is going to be very large. So you're going to have KIT of a variable, because this variable is going to go wherever it wants to go with the n. So let me look at KIT of Xi. So KIT of Xi, when Xi is less than T phi, it has 1 behavior. It's got 3 ranges. When Xi is between T phi minus T phi to the 1/3, T phi plus T phi to the 1/3, it's got a transitional range worked out by people like Watson very carefully. In the transition range, it looks like an airy function. And the analysis is all around this airy function. All the difficulties are connected with this airy behavior. And all the mistakes I've made, and many of them are always connected around here. That's why I put little t. It's very easy to forget the behavior in this transitional range. So the analysis involves this K-Bessel function, and especially the integration with off-diagonal terms and understanding when they are significant and when not, which is very subtle. And a lot of 19th century, hard work in 19th century saddle point method is quoted there. But people have studied this, and if you look at the literature, people will usually study this where this and this are different sizes, or this over that is roughly the same size. We need everything uniform. It was done beautifully by Dunster. All right, that's, and just to go back here, I'm going to talk about random in a second and finish. If you pretend these rho phi n's are random numbers, that would be your random wave model. But these rho phi n's are eigenvalues of the Heck operator. These are arithmetic beasts. So all the hard work here is to use all the arithmetic that you know to try mimic random and show. The question is, what can you prove for random? So there is, and this model would be good enough if you made those things random. But let's go to the following model, which is the one that is the only one that's understood by the work of Nazarov and Soden. Soden lectured on this here last year. And their theorem is not about an eigenfunction. They stated it for eigenfunctions, but they don't mean it. I see Soden there. He's going to go run and tell his dad, but I've had a discussion with his dad. This is about linear combinations of eigenfunctions, which on the sphere, where there's a high multiplicity, a linear combination of a short range is again an eigenfunction, which is absolutely not true here. So in this situation here, if you adapt their methods, and they have a paper which will do this, I think, but you can easily adapt it yourself. Instead of looking at the eigenfunctions phi j, let me look at a window, tj, between capital T. So this is what can be proved. I randomize the problem by, instead of talking about eigenfunctions in their 0 sets, a random function, which is band limited to have its frequencies tj between t and t plus 1. You can do this on any manifold. The answer is universal. It'll apply in our case. And then you're not going to look at orthonormal basis or an eigenfunction. You're going to look at this function and ask, how many components does its 0 set have, and is that connected to percolation? And in this setting, Nazarov and Soden prove a beautiful theorem. There's a universal number of nodal domain of level sets that this function will have in the Gaussian field with the CJs here, Gaussian. In this window, it won't depend on the manifold, and it will be a constant times t squared, where the constant is some positive number. They don't know what the number is. Whether that constant is the Bogomolny prediction or not is completely mysterious. They have no idea. Their method never touches percolation. So the entire belief in Bogomolny is based on numerics. The fact that his conjectured number seems to be right, even for the individual eigenfunctions.
So you don't expect this C to be the same?
The C in Bogomolny, I'm sure it's correct.
No. The C in Nazarov-Soden, you believe it's the same?
Of course, there C is the prediction. This I've had a student check, this constructing random waves, and it's good to 5 decimal places. Bogomolny's found a universal constant of nature. I'm serious. And it comes from this exactly solvable percolation model, and I can tell you in terms of how many ovals a random projective plane, real plane curve has even. Now, there's a universal number here, which is absolutely robust.
The same, although the argument does not tell you any connection.
The argument just is an existence at this scale of a constant. One of the hard things that you know very well is to prove their constant is positive. And to prove their constant is positive, they do so by a very clever construction of little loops, construction of a barrier that he explained here. I've gone over time. I think I should stop. I have some references, but thank you. I'll be happy to explain the details of the main theorem to anybody who's interested. You just contact me. Yeah.
Well, the main mystery to me is why the square lattice enters
Yeah.
this picture.
He has no.
Maybe you understand that.
No, I don't. I think I taught a course on it last year, and Belayev, who taught it with me, he had all sorts of ideas trying to explain the square lattice. I'm giving you, I think that the way Bogomolny came with it is the argument I gave you there, that whenever we have a crossing, the question in the end, why are we left with a square lattice?
Yes.
There's no good explanation of that I know.
You were about to give one I thought was going to be semi-plausible.
Well, I think that if you look at torus,
Cosines have
yeah,
the square lattice.
right, and then you perturb that with something that's going to be independent at each vertex, which is what you believe somehow this randomness is doing.
Yeah, you have the same theorem on the torus, so you could check it for the torus also.
The random. The random has been checked on the sphere and on in a number. So Bogomolny checked it in the plane, and his numbers were not so good. What I'm telling you, where it's been checked to great accuracy, is Nastazescu, a student of mine who took random linear combinations of spherical harmonics, and for every choice of degree 100, there's in Nazarov-Soden, not only is the theorem that the expected number is this number, but it concentrates around the mean. So you don't have to do many experiments. Yeah. Each experiment gives you the same. The fluctuation decreases exponentially. So she ran a few hundred examples, and the ratio was every time within 4 or 5 decimal places from the prediction. You can do the same on the torus. It'll be the same number. No. There's a theorem here. Soden and Nazarov show this constant is independent of the base manifold if you take linear combinations. So this number is universal. They don't show this, but they will show it in their next paper. But if you read their proof, it's this constant here that they produce here is universal. It's a universal number of nature in dimension 2.
In what sense?
In that if you take any Riemannian manifold whatsoever, and you take a band-limited function of this width. So let me repeat this. So this is why it's quite pleasing. So it could be a hyperbolic manifold, a torus. It could be anything you want. This is much softer. Take any compact Riemannian manifold. I wanted to say, what is a random function, real function on this manifold? Well, you have to grade it somehow. So I'm going to talk about a random band-limited function. Throw any metric on the manifold, and now use a metric to define a window. the window will be square root, so tj between t and t plus 1. That has about, by Weil's law, about t eigenfunctions. And then take this to be Gaussian.
Oh, those are Gaussians.
And then take the scale, then the...
They're
independent means 0 Gaussians. Then this generates a random function C on the manifold. Look at the 0 section of that. How many connected components does a random... If I take a random real function, how many connected components does it break the space into? Universally, a constant times t squared. So the band, it depends only on the width of the band. So in this band width here, this is the width that gives you percolation. So what Nastazescu checked, if you take a dyadic sum here, you'll get a different constant. It's interesting, and that constant, we don't know its connection with percolation. But on a short range, shorter than that, you can't analyze. That's the range which produces this universal constant. And that constant is universal, whether it's equal to 3 minus whatever it was, root 5 over... whether it's that number or not. That you're
I know very few constants of nature, no, but they're seldom algebraic.
right. It's amazing, yeah. So this is a remarkable thing that Baxter discovered in this.
What is known about eigenfunctions of, say, GOE matrix? If you take an eigenfunction...
No, there's no, that's not a continuum. You mean if you ask a random graph, I don't know, how many components does a random graph have? I don't know. Random eigenfunction on a large, I don't know about discrete stuff.
Let's talk about it.
I don't know about, we're talking here, so you're talking here about a random function. I have with Wigman a theory which is similar theory which connects with a constant, whether it's percolation or not, I don't know. For a random plane real projective curve of degree t, how many ovals does it have? And there's a universal answer. Aha. In your, not in yours. So there's a, on the space of polynomials, you put the real Fabini study, not the metric that you once put, which is basically they call the complex Fabini study, and not the naive model. In the naive model, there are very few ovals. So if you take a random plane curve of degree t, you'll only have log n squared ovals. If you want to have this constant times, if you want to have a constant coming close to Harnack's upper bound, which is like Courant's upper bound, you must take the real Fabini study, and then there's the same universal number. It's always universal. So the number's universal, but we don't know what it is. Yeah.
So these Nodal domains for the random function and for the percolation model, are these local? I mean,
No, they're mixed. That's a very good question. So in Nazarov-Soden, there are ones which are little loops, which are completely local, and then there are many long ones. And the totality converges to their constant. The way they prove their constant's positive is by making a positive proportion of little loops. But that's a very small proportion. The actual constant, Nastazescu explicated their proof, and the proportion, the proof that C is positive, right now the best lower bound we have is 10 to the minus 8. So the answer is they are mixed, and that's why they have never seen percolation in their argument, really. Their theorem is more like the existence at the right scale is universal. So they keep on taking scaling limits and eventually get a model field which is everything's converging to. And for that field, the answer is the answer for all guys in this window. So there's only one paper that you need to look at. That's Soden-Nazarov. That's rigorous. It's a beautiful paper, and you have to generalize it to the setting. Yeah.
Does this seem true that your functions have an influence on the, if you repeat the same percolation model with...
I don't know. Right. So I think in the percolation, they square root of the totality, so I don't think they have an influence. But I could believe that the arithmetic would have had an influence. And in many other problems where random prediction is one thing, we find like the quantum variance is very different. So I was very shocked to see that Bogomolny's constant just came out right by just coloring in and counting. That's what changed my view. And then Nastazescu is doing random calculations. You're absolutely right that if we wanted to explain what we're seeing at a finer level, we should randomize with the symmetry. But that's just square root of the totality. Most nodal domains are green, and they are not little loops. Because when the scale gets very large, you'll have a lot of these green guys which are quite long themselves. Now, there are maybe universal percolation things that come from conformal invariance in SLE. But as far as I can see, most of those things don't agree with the numerics. So I'm not believing any of that yet. Bogomolny goes to town. He says everything's explained by SLE. But his numerics are not convincing. Yeah.
I mean, your inert domains, if I got you right,